Another scheme that has sometimes been applied to the solution of complex networks is the nodal method or the nodal analysis. It offers the advantage that a minimum number of equations need be written to determine desired quantities. So, definition of nodal analysis: it is a method that provides a general procedure for analyzing circuits using node voltages as the circuit variables. Nodal analysis is also called the nodal voltage method. Some features of nodal analysis are: nodal analysis is based on the application of Kirchhoff's current law. Having n nodes, there will be n-1 simultaneous equations to solve. So if we have 3 nodes, 3 minus 1 is the number of equations. So we will have 2 number of equations. Solving n-1 equations, all the node voltages can be obtained. The number of non-reference nodes is equal to the number of nodal equations that can be obtained. So non-reference nodes will be the number of equations. Okay, so types of nodes in nodal analysis. We have the non-reference node and the reference node. Non-reference node, it is a node which has a definite node voltage, such that node 1 and node 2 or node VA, node VB, and so on and so forth are the non-reference nodes. It depends on what you will call the nodes. Reference node, it is a node which acts as a reference point to all the other node. It is also called the datum node or datum node. So this reference node will be zero voltage. Okay. So solving of circuits using nodal analysis. We have the basic steps used in nodal analysis. So number 1 is select a node as the reference node. So you will select datum node to be your reference node. Assign voltages V1, V2, or VA, VB, and so on and so forth to the remaining nodes. So the voltages are referenced with respect to the reference node. Apply KCL to each of non-reference node. So in order for us to apply KCL, you need to assume the direction of currents in branch circuits or branch circuits. Use Ohm's law to express the branch currents in terms of node voltages. Node always assumes that current flows from a higher potential to a lower potential in resistor. Hence, current is expressed as follows. So, as you can see, this is Ohm's law equation. So, we have I, which is the current. It is equal to the high potential minus the low potential voltage divided by the resistance or the connecting resistance between the two node voltages. After the application of Ohm's law, get the n-1 node equations in terms of node voltages and resistances. Solve n-1 node equations for the values of node voltages and get the required node voltages as result. So in order for us to solve the node equations, you will use algebraic equations, elimination, substitution, or even matrix. Okay, we will have an example for this node analysis for us to more understand the concept in solving this kind of theory. Example number 1. But before that, you need to remember this Ohm's law, yung kanina. So I will call it the tip to tail, our direction of current. The arrow is the tip and the tail will be this one. So as you can see, this is a while ago the V high minus V low divided by the R. So this is tip minus tail divided by the connecting resistance between the two node voltages. So in this circuit, we have two node voltages, and getting the number of equation in this circuit is n minus 1. So we have 2 minus 1 is we only have one equation to solve the node voltage of this kind of circuit. So first, you need to assume direction of currents, whatever you like. For me, we have the direction of current IA from node VB to node VA, IB from node VB to node VA, and IL node VA to node VB. So I call the node points to be VA and VB. And I set VB, this one, as my reference node. So this VA will be your non-reference node and VB will be your reference node. Next is you need to identify or formulate the equation, Kirchhoff's current law. So we have here the KCL equation. Entering into the node voltage VA, IA minus IL plus IB is equal to 0. So formulating now the equation, node VA, so this one node VA, from tip to tail, so we will extend this direction of current. It came from VB and it goes to node VA. So we have positive VB minus VA plus, of course, the direction of current enters into the negative sign of the battery. So you will have a positive 24 volts divided by the connecting resistance between the two voltages, which is equal to 0.4 ohm. Minus, so we will adapt the sign here, minus. So minus, the equation of IL now is equal to, IL is from VA to VB, so that is minus positive VA minus going to VB divided by the connecting resistance between VA and VB is 0.8 ohms. Okay, so plus here, the equation of IB from VB to VA, so that is positive VB minus VA, it enters into the negative sign of the battery, so that is positive 26, divided by the connecting resistance, which is 0.4 ohms. So you will equate this one to 0. Okay, so you already have the nodal equation. You will apply now your knowledge in algebra. So as you can see here, we have a negative VA, and negative VA. So we will set this negative VA and we will add all the connecting resistances. We will simplify this equation. So negative VA multiplied by 1 all over 0.4 plus 1 over 0.8 plus 1 all over 0.4 plus, of course, we have the voltage EA 24 divided by 0.4 plus this one plus 26 all over 0.4 is equal to 0. So solving for VA is equal to 20 volts. So here pala, yung VB natin is we will equate this to 0 kasi we set our VB as our reference node equal to 0. So naging 0 to. And then we will solve now your branch currents, which is IA, IL, and IB. The equation of IA is this one, negative VA plus 24 all over 4. We'll substitute the value of VA, which is 20. So negative 20 plus 24 all over 4, all over 0.4 is equal to 10 amperes. Next is your IL, VA all over 0.8. So 20 divided by 0.8 equal to 25 amperes. Your IB is 26 minus VA all over 0.4. That is equal to 26 minus 20 all over 0.4 equal to 15 amperes. We'll solve for the load power of the circuit. So PL is equal to IL squared RL or ILVL. Okay? So masasolve mo na yung load power in this kind of circuit. So IL is equal to 25 squared times RL is 0.8. That is equal to 500 watts. Okay? So I hope you understand our first equation. We'll now go to example number 2. Example number 2. So we have the same example in Kirchhoff's, Maxwell, and superposition. Now we will solve the branch currents using the nodal analysis. So first, we will identify the number of nodes. We have 1, 2, and we can make this as one node. This one. So we have now 1, 2, 3 nodes. I will call it VA, VB, and VC. And I set VC to be my reference node. So I will equate this to 0. And this VA and VB will now be the non-reference node. Next is the direction of currents. You need to assume the direction of currents. So I will assume my I1 to be this way, IA downward, I2, IB, and I3. Next, I will formulate the KCL equations on nodes VA and VB. So KCL at node VA. But before that, the number of equations in this problem will be, we have 3 nodes, so 3 minus 1 is, we have 2 equations only, which is the equation in VA and VB. So KCL at node VA is I1 minus IA minus I2 is equal to 0. The equation for I1 now will be from VC to VA. So that is from VC positive minus VA. And then entered into the negative sign of battery. So plus 120 divided by the connecting resistance between VC and VA is 1.5. Minus IA, equation of IA is from VA to VC, so positive VA minus VC divided by 21. Minus I2 is from VA to VB, VA minus VB divided by 3 is equal to 0. So VC is equal to 0. We will set this 1, 0, 0. So walang VC dito. And we need to simplify this equation. Negative VA, and negative VA. So combining like terms, we have negative VA multiplied by the sum of the connecting resistances. 1 divided by 1.5 plus 1 all over 21 plus 1 all over 3 plus VB is negative here and then negative VB, so you will have positive VB all over 3, then 120 divided by plus 120 divided by 1.5, so wala na, is equal to 0. This is negative 1.048 VA plus 0.333 VB plus 80 equal to 0. So VA is equal to 0.333 VB plus 80 divided by 1.048. So this will be my equation 1. KCL node at VB. VB. So KCL node at VB. We have I2 minus IB minus I3 is equal to 0. Equation for I2 is from VA to VB, that is VA minus VB all over 3 minus IB is VB minus VC all over 6 minus I3 is from VB to VC. So VB minus VC entered into a positive sign of the battery. So minus 105 divided by 1.5 equal to 0. Simplifying this equation, we have VA all over 3 minus VB times 1/3 plus 1/6 plus 1 all over 1.5 plus negative here and negative, so that is positive 105 divided by 1.5 equal to 0. Simplifying this equation, we have 0.333 VA minus 1.167 VB plus 70 equal to 0. This will be our equation 2, and we will substitute equation 1 and equation 2 in equation 2. So 0.333 times 0.333 VB plus 80 divided by 1.048 minus 1.167 VB plus 70 equal to 0. Multiplying both sides by the denominator 1.048, we have 0.111 VB plus 26.64 minus 1.223 VB plus 73.36 equal to 0. Solving for VB, we have 89.928 volts. Substituting the value of VB in our equation 1, we will get the value of VA, that is equal to 104.91 volts. These are the final answers for the branch circuit currents. We have I1, the equation is this one, negative VA plus 120 divided by 1.5. That is approximately 10 amperes. I2 is VA minus VB all over 3, which is approximately 5 amperes. IA is VA all over 21. That is approximately 5 amperes. I3 is VB minus 105 divided by 1.5, approximately negative 10 amperes, and IB is VB over 6, it is approximately 15 amperes. If you have any questions regarding our topics, don't hesitate to message me or comment down below your questions and I will try to answer as much as I can. Thank you.